Well, it's fantastic to be here at the IAS, have the opportunity to speak to you all about some physics. I don't think it'll be quite as much as a high point, maybe, as the thanks to all the amazing staff that we just enjoyed. But in any case, I also have well, I've started here with a little overview of the lectures I'm going to give. I'll start with now a lecture on gravity amplitudes and the double copy. And then the next two lectures, I've already been scooped by Simon, who managed in one lecture to cover almost everything I'm going to do. Well, that's not true. In fairness, Simon has introduced and provided some really nice theoretical underpinnings for the story I'm going to give in these lectures about classical observables that we can compute from scattering amplitudes. One of these is called the impulse. That's a little connected to this 6-point object that Simon was just talking about. And then in the third lecture, I'll discuss the waveform. So I'm really going to be interested in the classical gravitational waveform set up in some scattering process. So I'll make contact with Simon's lectures there. So he didn't completely scoop me. Probably just tried. Simon for you. And then the fourth lecture, I'm probably going to talk about observables at one loop. I might vary that depending on how things go and my activation energy for writing another lecture. We'll see how it goes. Okay, but I want to start with giving you a little bit of motivation, right? So I'm going to be telling you about amplitudes in gravitational theories and specifically about classical applications of them. So you might wonder, why do I care about these things? You know, we're here at a conference in school about scattering amplitudes. Scattering amplitudes are objects in quantum field theory. Why would you want to use them for something in classical field theory? It seems completely backwards. When you started your undergraduate degree, you know, people didn't start off by telling you, lecture 1, quantum field theory. We're going to use that to understand dynamics of point particles. Not what we do, right? We actually start with a lecture on classical dynamics of point particles and eventually get to quantum field theory. So why am I doing it the other way around? That's one question you might ask. Well, my point of view is that in our field, in scattering amplitudes, we're really good at perturbation theory. We got really, really very good at perturbation theory. Now, we'd like to go and use what we've learned to challenge ourselves and compute some interesting new quantities, you know, physical observables, things that we can compare to nature. So that's one motivation, you know, we're good at perturbation theory, let's go ahead and use it. Right? At the same time, we're hoping to challenge ourselves, right? So push our techniques as far as we can go and see what we learn, you know, take them, you know, if you do an honest calculation, you finish it off, often you'll find something, learn something about the structure of the scattering amplitudes from performing that computation. So it's not just about, you know, computing observables, it's also about learning about the amplitudes themselves. And maybe we'll see some examples of that in these lectures. I said that we're really good at perturbation theory, but of course we're not the only people who are really good at perturbation theory. There's a lot of fantastic other physicists out there who have got a tremendous wealth of knowledge. And gravitational physics is an example. There's been many years of people studying gravity, both in perturbation theory and non-perturbatively, and we can learn from these people. Right? So we can learn about amplitudes by making contact with people in other fields and importing knowledge from their experience. Gravity is also an interesting field to think about at the moment because it's very vibrant. There's a lot of work going on learning about, well, there's gravitational observatories being built around the world, a lot of money being spent on these things. It's, you know, so a lot of work being performed on this kind of science, and it's fun to get involved with this. So there's a variety of different motivations for thinking about this. Okay, let's see. Anything else I wanted to say? Yeah, okay, good. So today I'm going to start with a little discussion about computing gravitational amplitudes and a brief introduction to the double copy. Right? So the point of this is just to, well, it feels very strange to have a whole series of lectures about using gravity amplitudes without actually computing any. So let me start by computing a couple of amplitudes and then we'll build on that. So by the way, I also, like everybody else during this course, I think I welcome questions during the lectures, right? So just interrupt. Okay, so let me start by talking about some gravity amplitudes. Or amplitudes, grams. Okay, so I'm going to start with some very simple examples and then build up. Right? I'm mostly going to be interested in examples where I have some massive particle, because those are the kind of amplitudes I'll need to use later on. So let me start with the simplest possible thing. So this is the 3-point amplitude. So 3-point amplitude for a massive particle. A massive particle. And gravity. Okay, so the picture is I have a massive particle with some momentum p, and some interaction comes out with some other momentum. I call it p prime, and the particle interacts with the graviton, right? So the gravitons are going to be the double wiggly lines. So let's say that comes in with some momentum k, and it has some polarization tensor e mu nu. So then this final momentum is going to be p plus k. Okay, so now one could go ahead and compute the amplitude for this thing. It's pretty straightforward by writing down the action, the Feynman rules, and you can do that calculation. However, it's far simpler to just write the answer down. This is one of these, Feynman has this business about how in physics you should state the problem and think real hard. You don't have to think real hard here. You just have to write it down. It's very easy. One thing that really helps is to note that you can always write polarization tensors for gravitons in terms of a bunch of polarization vectors, 2 polarization vectors. So this we can always do. Right. So why? Well, this polarization tensor has to satisfy a bunch of properties. It should be traceless. E mu mu should be 0. And both of these things are on the right-hand side. These things here are both traceless automatically because epsilon squared is 0 for a plus or a minus polarization. Polarization tensors also should be symmetric under interchange of their indices, and these things are symmetric. And finally, they should be gauge invariant in that k mu, e mu nu should be 0. Where k is the momentum of the graviton here, and these things automatically satisfy these properties, right? So I've just given you a basis of 2 things that satisfy all the properties of polarization tensors. So they're a basis. Everything else is gauge equivalent to them. And it's very handy to use this decomposition, right? Okay, so to write down this amplitude, m, I'm going to call the amplitude for this thing an m. Well, we need to make a list of scalars, right? There's some sort of scalars we can write down, and what are they? Well, I can write p dot epsilon for a plus or a minus. That's a perfectly fine round scalar. But p prime dot epsilon, p prime, that is equal to p dot epsilon, because the difference between p prime and p is just k, and k dot epsilon is 0. Okay, so these are scalars. Remember, for a gravitational amplitude in Einstein gravity, I have to write 2 momenta, right? I need 2 momenta. I need 2 p's. I need 2 epsilons, right? P squared is m squared, p prime squared is m squared. And there's not many scalars we can really write down. So it's straightforward to see that this amplitude can only be epsilon.p squared, right? So there's some number there. So really, it's just, it's by exhaustion. That's the only possibility. That must be the amplitude. The number here is going to be something involving a constant kappa. So kappa, I'm going to define kappa to be kappa squared to be 32 pi g Newton. And basically kappa is the inverse of m Planck. Okay, so it just boils down to figuring out what the number is. Of course, the number is just basically the definition of these couplings. So yeah, we just need to make sure the number is consistent with other facts we know about physics. I'll get that number right in a moment. First, let me make an observation, which is that there's a relation to an amplitude in Yang-Mills theory. So there's a connection to an amplitude for a massive particle So in Yang-Mills theory, so I mean a minimally coupled particle. Okay, maybe I will try to leave some of those beautiful boards untouched. Okay, so now if I consider a massive particle in Yang-Mills theory, so here's the same picture, except now with a gluon here, a gauge boson. Right, so momentum K, and the polarization epsilon, and it gets a color A. This amplitude is G times TA. Well, this is one that one can write down using, well, you can use the same methods. It's got to be an epsilon.p. It's the only scalar that's running around the place. To get the normalization right, I happen to know, because I did compute it with Feynman diagrams, that there's a 2 there. We usually use well, in this context, we often use a different normalization of the t's. So there's a root 2 that gets absorbed. So this is just a normalization. And now, well, it doesn't really matter which we look at, but this is the one which is standard. If I compare this amplitude in Yang-Mills theory to this one in gravity, well, you can obtain the gravity one from the Yang-Mills one by replacement rules. So we replace G with kappa over 2, and then the color factor here, T tilde A, with the rest of the amplitude, the kinematic part. So then you get the gravity amplitude, which is then going to be, well, there's a kappa over 2. The 2's get squared, so there's a 2 epsilon.p squared. So it's just kappa epsilon.p squared, and that's the correct normalization. Okay, so this is a basic example, perhaps it's the most basic example of what people call a double copy. The double copy is one method of cooking up amplitudes in gravity from amplitudes in Yang-Mills theory.
Just to make sure, we're talking about massive scalars over here.
This is a massive scalar, yes. So the question was, are we talking about massive scalars or other particles? But yeah, this is a massive scalar amplitude, exactly. Yeah, thanks. Yeah, one thing that's interesting about gravity amplitudes is that we don't understand them super well. This double copy is one method we have to cook them up, but maybe some of you in the audience will find other methods, and that would be fabulous. Yeah, please.
Yeah, hi. I just wanted to follow up on the 3-point gravity scattering amplitude that you calculated. So, like coming from the Feynman rules, you would also get like a term that's, I mean, if it's like a massive scalar field, you would also get a term that would lead to like a trace of the epsilon tensor times the mass.
Yeah.
that like
but
here
the trace of
doesn't.
the epsilon tensor
Yes,
is 0.
here doesn't contribute, but like when you have at least two gravitons, like a 4-point function, then you would get also like the cross terms of the two polarizations, right?
Yeah,
Is there like a physical reason why the mass term like doesn't contribute at like a 3-point, but does contribute at 4-point?
A physical reason. I don't. Yeah, I mean, it's
It
an
does seem a
interesting
bit
question.
strange
Yeah,
to me. I don't know.
yeah. I mean, indeed, you might. Yeah, in a way, this is precisely why I did the computation this way. Because if you do go ahead and write down the Lagrangian, yeah, you've got this square root of the metric. You've got to expand it. It's this trace. Blah blah blah. There's some story about it, and you find, oh, it doesn't actually contribute. The same with the conformal coupling term. If you wanted to include that, it doesn't contribute at 3 points. So now why does that happen? I guess it's just because these 3-point amplitudes are so simple. Now, it's not that it's completely gone, right? I mean, it's still true. Why can't I find it? Yeah.
But like here, it would be the same for massless and massive,
well,
right?
you know, the
at 3
difference is
point?
that p squared is m squared, right? You know,
Okay,
of course, maybe that's, but yeah, I mean, I don't have any deeper reason than I can't write down something that actually does it. And you are right, of course, that they will contribute at higher orders. I'll make some remarks maybe about how to capture some of those effects later.
Okay, thanks.
Yeah. Any other questions? Yeah.
Just like, silly question, but
There's no silly questions.
you're doing this replacement with like this, T tilde, which is like a color factor,
Yeah.
and you're replacing with like kinematic information like epsilon dot p.
Yeah.
It's like how, I don't know. It seems to me that one thing is color, like has to do with like the group theory structure.
Yeah,
and
exactly.
another thing is like kinematic information. Like how,
Yeah. They seem totally different.
yeah, what's up with that?
Yeah. Well, that's a fantastic question. Maybe this will become even more stark towards the end of the lecture. So maybe I can clarify it a little bit then, if you don't mind. But yeah, I mean, this should always be. Well, maybe I can make some remarks. Somehow, this double copy is inviting you to think that the kinematics is in some way similar to the group structure. And that's maybe a recurring theme in gravity, that somehow, gravity wants to be some kind of a gauge theory, but where the gauge group is something to do with kinematics. So this is maybe one of the ways in which you can begin to see an inkling of that. And we'll see it more later on.
Thank you.
Okay, great. Okay, so good. So we've computed our first amplitude. It was a pretty wussy one compared to what Fabrizio is computing. Obviously, this is really, pretty crappy. Okay, well, let's try to do something a little bit more challenging. So it's not. I'm still going to stay in the domain of 3-point amplitudes at 3 levels, but maybe a little bit more complicated 3-point amplitude. So the 3-point gravity amplitude. Okay, now this is something that is really simplest to write down if you use the language of spinor helicity. I'm not going to do that because, that's one thing I've noticed is that there hasn't been a lot of spinor helicity at the school so far, so I'm going to follow in that tradition and avoid it. This is also probably the only point in these lectures where it could be convenient, so I'm going to just avoid it. So let me just remark that this 3-point amplitude in gravity is really the amplitude that we get from the Einstein-Hilbert Lagrangian, right? Yeah, so from SEH, that's the Einstein-Hilbert Lagrangian. Try and make these E's and H's bigger. Now, the point about this is that's unique. The unique true derivative thing I can write down with 1 over m Planck. Okay. So now let's see. So let's start with a picture. So here's a picture. So 3-point amplitude. So that's a vertex. So I'll have 3 particles coming in, K1, K2, K3, and they all have various polarization tensors. I won't bother showing the polarization tensors. Okay, so now as a first step to writing down this amplitude, what I'm going to do is start by thinking about the equivalent situation or the related situation in gauge theory. So let me draw a little arrow. So I'm going to pass to the gauge theory. So we often, in this context, talk about the single copy. You know, the double copy is going from Yang-Mills to gravity, so going the other way is, well, it's the single copy. We don't have very sophisticated nomenclature in this field. We've got double copy, single copy, and sometimes the 0th copy. That's as far as we go. So in the single copy, there's 3-point amplitude for a bunch of gauge bosons. Okay, and these have colors. You know, well, let me put in colors A, B, C, that's easy. Okay, so now this is an amplitude that is easy to write down. Again, you can look it up in your textbook, or many of you probably know it off, but we could do a similar procedure to what I used here, you know, just enumerating the possibilities. There really aren't very many. In Yang-Mills theory, I better put in, you know, one derivative. And so I'm going to have one momentum in my amplitude. I have to put in a polarization vector for all 3 particles. I have to have Bose symmetry. So the scalars, the list of scalars is something like, I could have epsilon 1 dot k2. Right? I can't write epsilon 1 to k1, that's 0. Epsilon 1 dot k3 is minus epsilon 1 dot k2, because k3 is minus k1 minus k2. Right? So I can write this scalar, it's got one momentum. I can write another sort of set of scalars, epsilon 2 dot epsilon 3. And now you've already exhausted the kind of list of things you can write down. Nothing more we can do. So you just have to make your amplitude up by multiplying enough of these together and adding them up to get Bose symmetry. Right? That's all you can possibly do. I've put in a color factor as well. So let me write it as A, B, C. Well, there's a coupling. Let me put in the color, that's obvious. It's got to be the FABC. And then I can write epsilon 1 dot K2, epsilon 2 dot epsilon 3. And once I've written that, I have to start enforcing Bose symmetry. And you can do that, well, the only way to, well, you can just add the remaining cyclic permutations plus epsilon 3 dot K1, epsilon 1 dot epsilon 2. That's the only possibility up to a number, right? And the number is, so this has, well, there's some conventional normalization there. Happens to have an I in it, and maybe a minus sign. I'm systematically going to ignore almost every minus sign in these lectures, but that is one that I looked up, so I managed to remember it. Okay, but yeah, so it's fixed up to that normalization just by general considerations. Okay, so now how can I construct the gravity amplitude? Well, there's some color stuff. I mean, there's some normalization. There is actually a similar thing that people tend to do with the FABC. There's like a tilde FABC, there's another root 2. I'm going to ignore that here. But the algorithm to get the amplitude in gravity is going to be replace G with kappa over 2 and take the FABC and replace it with another copy of the kinematics. So that is at least a double copy. Let's say it suggests, because, you know, we need to worry about these things. So that the relevant amplitude would be a kappa over 2 up to a normalization. I'm not going to use this, actually, funnily enough, this 3-point amplitude again, so I didn't bother getting the normalization right here. So epsilon 1 dot K1, oops, plus cyclic squared. Right. Now, you might wonder whether that's the right amplitude. You know, I just replaced some kinematic thing with I just replaced some color thing with a kinematic thing. Did I do it right? You know. So, well, what do I need to check? So, is this the right amplitude? Is this the correct amplitude in GR? So, okay, so a couple of observations. Firstly, it has the correct, let's say the correct helicity structure. by which I mean these polarization vectors here. They're coming in pairs, which I could reassemble into polarization tensors. Right? So I really have polarization tensors associated with 3 external gravitons. So I've got the correct external states. So I'm happy, right? So in other words, good states are okay. Let's say states work. So a second observation is it has the correct power counting in momentum, right? The Einstein-Hilbert action has 2 derivatives, right? It's always 2 derivatives on some bunch of metric perturbations. So it's the correct number of momenta. So that's working. Is there anything else to say that's correct about this? Yeah. That's right. So a third thing, actually something I should have said over here, is this amplitude in Yang-Mills theory has to have the property of gauge invariance. Right? So the ward identity means if I replace one of these epsilons with the momentum, then the amplitude has to vanish. Right? And it's straightforward to see that that happens here. So, for example, I replace epsilon1 by k1, then this term will just vanish because k1.k2 is 0. That's a property of 3-point kinematics. k1.k2 is a half k1 plus k2 squared, and k1 plus k2 is minus k3 by momentum conservation. So this thing is minus a half k3 squared, and that's 0. So that term would vanish, and these terms now will cancel one another. So I replace epsilon1 with the k1, well then, well, yeah. Let me see. So this would be epsilon3 dot k1, and this would be k1 dot epsilon2. Yeah, so this epsilon3 dot k1 is in common there. That epsilon2 dot k3 is minus k1 dot epsilon2. So the terms cancel, right? So anyway, that's pretty obvious, right? The amplitude is gauge invariant in Yang-Mills theory. And by just squaring it, I've carried that property over. So this is a gauge invariant amplitude. Okay, so in short, it's a gauge invariant amplitude of 3 gravitons, which has the correct power counting to come from the Einstein-Hilbert-Lagrangian. Since Einstein-Hilbert-Lagrangian is the only thing you can write down with 2 derivatives, this must be the correct amplitude. Up to normalization. So it's good, that works. Okay, so very good. So now I've exhausted pretty much everything I know about 3-point amplitudes, so let's go on to 4-point amplitudes. Try and use the lethal stick. Good. 3. Okay, so this is going to be a discussion of a 4-point amplitude involving massive external particles. Again, scalars. So massive. So the picture will look like this. So these are 2 different scalar particles which are interacting through gravitational exchange. So some momentum P1, some momentum P2, and here's some momentum P1. I'll say that they exchange momentum Q. Okay, so I want to compute this amplitude. Well, I'll start by computing the single copy amplitude. So I'll pass to Yang-Mills theory. So this is the single copy. Single. So the exchange Q, P1 plus Q, P2 minus Q. All right. Now, so this amplitude is probably, well, we can construct this in a couple of ways. We know what the 3-point amplitude is in Yang-Mills theory for the massive particles. You see, or did I write it? Gosh, I'm blind. Anyway, yes, it's right there. So I could use that. But honestly, in this case, it's probably, this is a very simple amplitude. You might as well just compute it with Feynman diagrams. And the result, well, so if I write, let's write the amplitude down here. So the amplitude for this thing is going to be a minus sign, a g squared. There is going to be color factors for these two particles, particle 1 and 2, which I'll just tie together. T1a, T2b, a. And then, well, this vertex here, so well, maybe I'll tell you what the vertex is. So the Feynman vertex is just 2p plus p prime here. So I will get a factor, well, from this one, 2p1 plus q. Oops. And from this one to p2 minus q over q squared. Okay. Very good. Good. Okay, so so this amplitude, let's see. So can folks see this? Yeah. Nope. So this amplitude then is, I just want to tidy this up a small bit. So firstly, I'm going to put the t tildes of minus g squared, t tilde 1a, t tilde 2a. So there's a factor of 2 downstairs. And then in the numerator here, there's going to be a 4p1.p2 plus, well, there's something of order q squared, which I'm going to neglect, over q squared. Okay, well, now that plus q squared, so this order q squared term here, comes about from several places. There's a minus q squared there, it's obvious, but then there's also a 2p2.q and a 2p1.q. These external states are on shell, so you can replace these 2p1.q's and 2p2.q's with other q squares, right? And all of those are just going to be absorbed into this order q squared term here. Now, I'm going to neglect contacts here. Contact diagrams amongst massive fields. So what I mean by that is I'm going to neglect, it could be a term from the Feynman rule that looks like this. So just if I entered some Feynman rule that made these particles actually self-interact at a point, I'm going to leave that out. I didn't write it down here. I could have put something in there. And this order q squared term here, it cancels that propagator, so it contributes something like that, right? Now, I'm going to neglect these. So we'll see why tomorrow. But the brief explanation is when I go and apply these amplitudes to classical phenomena, they don't contribute. So it's a classical simplification. But you'll see that actually happen tomorrow. This is a big win because capturing terms like that can be tricky. Right? Well, here I just get to ignore them. One of the reasons why classical amplitudes is nice. Okay, so very good. So let's then write down a candidate amplitude in gravity, which is obtained from this Yang-Mills amplitude by the double copy. So I would try and just on the basis of this, well, I'm supposed to replace this g squared by kappa squared over 2, kappa over 2 squared, that is. A minus sign there. I'm being sneaky about this minus sign, by the way. You know, in the world of scattering amplitudes, for a long time, people kept saying, you know, that the phase of the amplitude is unphysical. So nobody ever cared about the sign of this amplitude. But this amplitude actually is related to a physical quantity. As Simon said, there are observables out there that are linear in these quantities. And then you do care about their overall sign, their overall phase. Anyway, so here I'm putting in the minus sign because I know it happens to be the right answer. You have to be careful about getting these signs right. Conventions differ. There are resources for systematically getting these signs right. I'm not going to go into it here, but this one I know is a minus, so let me just put it in. Okay, so now let's see. So there's a factor of 4 there from that half, which I need to worry about. Something's telling me that there's a problem here. Okay, and then there's 4p1.p2, which I'm supposed to square and divide by q squared, plus order q squared, which again, I'm going to neglect, okay? Okay, now this question is this amplitude correct? Yeah. Okay, well, a very useful thing to do is to look at its factorization channel, right? So, well, let's say to test this amplitude, so what I mean by that is I'm going to take the limit as q squared goes to 0 of q squared times this amplitude, this n. Right. So what's supposed to happen in that limit is that this diagram here is supposed to split, right? Because I'm putting this internal line on shell. So this should be right. So in the middle here, I should be getting 2 3-point amplitudes, right? Summed over the helicity, the physical helicity of the states that are propagating. And I cunningly computed already the 3-point amplitude up on the top board there. So I know what I should get when I perform this operation. So let's see what we actually get, right? So, well, from here, okay, well, there's some 4s and some junk, which I'm just going to ignore. The q squared goes away. So the only non-trivial part here is this p1.p2 squared. Now that p1.p2 squared, I cooked up from this calculation. This was a calculation in Yang-Mills theory. So we know in Yang-Mills theory that when we factorize, you know, because, well, this was a bona fide computation. We know that when if I take this thing, this Yang-Mills amplitude, and I take q squared equal to 0, it will factorize onto a product of 2 Yang-Mills 3-point amplitudes. So this will become a sum on helicities, so the physical helicities of the particle, times p1 dot epsilon, h, that's the helicity of this particle, q, times p2 dot epsilon h of q conjugate squared. So that follows from the Yang-Mills theory. You know that the Yang-Mills theory factorizes. It's also easy to check this if you want. Maybe I'll make some remarks about that in a moment. Okay, so maybe I will use some of these boards. Yep. I don't square amplitudes. I square the numerator. Yeah, that's actually, okay, excellent. Thank you. This is something I should have been clear about. So what I'm supposed to do is replace the color by, you're supposed to kill the pole in each channel and replace the kinematics for that channel with the corresponding color factor. So yeah, so I don't want to square this pole because I know that in gravity, the propagators are the same, 1 over p squared type propagators as they are in Yang-Mills theory. So you don't touch the propagators. You're always just touching the numerators of the propagators. Yeah, thanks for the question. Yeah. Okay, let me just continue this equality over here. Well, let's write this. So lim q squared goes to 0, q squared m is going to be, okay, well, let me just write out some terms here. So there's going to be a term which is p1 dot epsilon plus of q. I'm just squaring things, so I can square that. Squared p2 dot epsilon minus of q. So the complex conjugate just flips the helicity. Squared. So that's one term. There will also be other terms which look like p dot epsilon plus of q. Just because I'm squaring everything out here, there will be p1 dot epsilon minus of q times p2 dot epsilon, say minus of q. Oh dear. P2 dot epsilon plus of q, and plus other terms. Right, so I haven't written all of the terms here. Right? Now the point here is this thing is a 3-point amplitude in gravity. So it's of that form there. It's epsilon dot p squared. So that is a GR amplitude. And so is this. It is p dot epsilon squared. But these aren't. Right? This has got p dot epsilon plus times p dot epsilon minus. It's not an amplitude. It's not, this shouldn't happen if you have the scattering between these massive particles mediated purely by GR. Right? So what's happened here is some other particles are appearing in the factorization channel. Now these particles, this thing here, p1 dot epsilon plus times p1 dot epsilon minus is not a GR amplitude. So I don't know whether you want to put a sad face or something there. So we learned something, right? You've got to be a little bit careful when you're doing these squarings. What I've really done here is I've started with Yang-Mills theory, and I've developed an amplitude in a theory which does involve gravitons, but also has two other particles, which people call the axion and the delta. So this amplitude in GR plus axion plus dilaton. So it is not a GR amplitude. Okay, now there's a fix. Well, maybe there's a couple of remarks. So I have yeah, so an exercise for you. So the exercise, well, it's an easy one. So you can repeat this construction in d dimensions. And the interesting thing is to figure out what happens to the axion and the delta. Okay, are there any questions about that?
Just one like general question. I don't really follow the logical chain here. So starting from this Young-Mills amplitude, I don't see how like the next natural step is this like educated guess in some sense. And then based on this, also this next logical step of going in the on-shell limit. So it seems to me a little bit ad hoc. I mean, just yeah.
Yeah, I mean, in Amplitudes, educated guesses is one of our best tools. It's called writing an ansatz. So you write an ansatz which encodes everything you know about the physics, and then you try and impose restrictions on it so that you get the right answer. And this is basically that idea, right? So I'm writing an ansatz, which gets informed by Yang-Mills theory. I know, because I understand how Yang-Mills theory works, that when I square these numerators, I will upgrade the Yang-Mills vectors being exchanged to gravitons plus potentially other stuff. So by looking at the factorization channel, you're trying to see if there's any weeds, anything bad that happened when you just did the simple square. That's the basic idea.
Okay, thanks.
So we know that so in CHY, double copy has other than the gauge theory amplitudes, it also has this bi-joint sector. Are these additional terms perhaps related to bi-joint scalar field theory? That also plays a role in double copy.
Yeah, okay, yeah, so indeed, the double copy can be implemented in various different ways, and CHY is certainly a way of implementing this idea, this double copy. In CHY, the bi-joint scalars play a clear role. It is indeed true that it's useful to think about scalars in the double copy. So that's what I mean by this zeroth copy. And I would say that CHY really captures that. Maybe I'll say a little bit more about that in a little while. But in terms of getting rid of these axions and dilitons, no, it's not subconnected.
Thanks.
I have a question about when you take the polarization for spin 1 and kind of mash them together to be spin 2. The word identity for spin 1 is exact, and then when you square them, you get higher order terms. So is it always going to work out? Doesn't matter the higher order terms, or the word identity is always satisfied? Have you just satisfied the leading order word identity for spin 2?
Well, I mean, I definitely want to impose an exact word identity, both in Yang-Mills and in GR. So when you have dangling legs, dangling gravitons or Yang-Mills legs, then you do need the word identity to be solved to all orders. And otherwise you won't get the correct physics.
Oh, wait. So in this case, we're just checking the leading
Well,
order.
here life is a little bit easy, right? Because I don't have an external graviton. So the word identity kind of goes out the window. So, it doesn't play such an obvious role here. I mean, it is appearing in the factorization channels when you go onto the pole. But there, because I've set up on the factorization channel that the simpler amplitudes satisfy the word identity to all orders, again, you're guaranteed that should work. Yeah. So you need it to all orders.
Okay. Thanks.
Hi, I quickly wanted to ask, so when you derived or related the 3-point graviton vertex to the Yang-Mills vertex, so when you derive Feynman rules for GR, it very much depends on how you define the graviton field. Typically you have G is equals to eta plus H. But there's also the other approach where you set the inverse metric density.
Yeah.
Here you got the case for the first case.
Well,
is there also a way to get a second one? I mean, the transformation property very much depends on that, because one is the tensor density, one is not.
No, but the amplitudes are invariant under the choice of your field. So amplitudes are field redefinition invariant, so it doesn't matter what field, what interpolating field you use. You're always going to get the same amplitude.
Okay, but the longitudinal properties depend on that. One is the transformation
not on
for
shell. So when you take any of these things and you put them on shell, they'll always satisfy the same properties.
Okay, that might be true.
Yeah.
Hey, you mentioned at the end that you're going to talk about things in D dimensions, but one of the naive things that goes off in my head is that the gravity has more than 2 propagating degrees of freedom in higher dimensions.
That's right.
So then why would I even expect things to work generally?
Well, first, why? Well, you can certainly make things work, but you have to do a little bit of, you just got to do a little bit of tensor algebra to see that it works.
Okay.
Yeah. So it does work out, but yeah, as you say, because the number of states changes and these things change in various ways. But yeah, so when I say things change, it's all just, you know, I mean, here in 4 dimensions, the axion and diletton are both scalars, but you'll find in higher dimensions that they're not scalars. Not both.
Thank you.
Okay. Okay, so just some general, let me see. So firstly, an important thing to do is to patch this issue up. So let me do that. So I do want to talk about amplitudes in gravity. So how am I going to fix this problem? So here, we found a problem that we got amplitudes that weren't in GR. Okay. So there's a simple thing to do. So the simple thing to do is just to replace the quantity p1.p2 squared in this amplitude here, right? So that p1.p2 squared isn't quite what I want, because we saw when we do this square here that the helicities don't, that we pick up these other amplitudes. But it is simple to fix that. So to replace that sum over helicities with this one. P2 dot epsilon h complex conjugate q squared. It's a small difference. Here, the sum is outside the square. Here, the sum is inside the square. Right? That's the only thing you need to do. It's a question of whether you square before you sum or sum before you square. Here, in this sum over helicities, I'm arranging that the helicity of this particle is always getting squared. So there will be a h plus. Well, that's going to get squared. I get p dot epsilon plus times p dot epsilon plus. And the same for the other side. So this is the correct property on a factorization channel in GR. Now, I will leave it as an exercise to show that this thing is p1 dot p2 squared minus a half m1 squared m2 squared. So the correct amplitude in gravity just replaces the p1 dot p2 squared here with this. Okay, and I'll use that in the next lecture. Okay, so now, so what is the general procedure here? The general idea is if you want to compute an amplitude, it could be some complicated amplitude, one strategy for doing that is to cut it, to take that amplitude and cut it to trees, or to simpler trees. So for example, here I was looking at a 4-point tree amplitude, but I just considered a factorization channel, namely I cut the internal graviton, thereby taking a complicated amplitude. Well, it's not terribly complicated, but this is a more complicated amplitude, and I related it to simpler amplitudes, which I already know. Right? Once you have constructed these simpler amplitudes, one can sum over the physical states to build up the expressions that you need for an amplitude in the full theory. This works very well if you don't have to worry about situations where you don't have these propagators, situations where you don't have contact terms. So if I had a contact term, this order q squared piece here, if I really cared about that, then you'd have to work harder to actually include the correct contribution of that contact term. So then you can use other methods. Maybe you need to use other methods. For example, BCFW is a method for constructing tree amplitudes where you don't have to worry about these issues. But you don't always have BCFW available. So this is a useful method for actually building up complicated amplitudes that you might need. I talked about this at tree level, but there's nothing about this that's tree. Right? you can use the same method for loop amplitudes. You can use it at any number of loops. What you need to do is be very careful about bookkeeping all of the channels that you're cutting and making sure that you're taking account, that you're correctly capturing all of the cuts and not double counting contributions. So, and that, that brings me to a talk at the conference last week. Zvi Byrne mentioned a method he has for, a new method, for simplifying these cut contributions at any loop order, right, to streamline that computation. So that's an interesting thing to learn more about. Anyway, so this is actually the practical way people tend to compute amplitudes in gravity. Okay, now I only have a few minutes remaining, and I wanted to make a couple of remarks on another, on a related approach to amplitudes in gravity, called the BCJ double copy. Okay, so I'll have to be brief. It's lunchtime. Okay, so BCJ double copy. So this is a method for computing amplitudes, tree amplitudes. Well, I should say tree or loop amplitudes. I'll talk about the trees, but the generalization to loops is pretty obvious. The generalization to loops is, however, conjectural, I guess. Okay, so the idea is that you start you take an endpoint tree in Yang-Mills. So I'll write it like this. So a sum over some diagrams. The diagrams always have to be cubic diagrams, which is to say with 3-point vertices. Right. So you can always do that. You can always write diagrams in terms of 3-point vertices. If you've got 4-point contacts, you can just introduce a fake propagator by writing p squared over p squared. Okay, now, if you consider a gauge transformation, so pick some polarization vector, say epsilon1, and replace it by epsilon1 plus alpha k1 for some alpha that you just pick. So it's just a random number. Well, then what happens is that these numerators are not invariant. The numerators change. Right. So the delta I are non-zero. Yeah. But the amplitude is still gauge invariant. Right? So now gauge invariance let me see, I'll keep this line, implies that the sum of Ci delta I over di, this quantity always vanishes. Now, this quantity always vanishes independently of the numerical value of these color factors. Right? These Ci's, I mean, ultimately there's some kind of number. But this works for any gauge group, and different gauge groups cook up different Ci's. So this identity only holds because of generic properties of all color factors. And those generic properties are two. So one is Jacobi identities. Color factors satisfy Jacobi identities. And the second are antisymmetry properties. So these color factors sometimes satisfy antisymmetry properties. So, okay, now suppose we find a set of numerators such that ST Ci plus Cj plus Ck equals 0. So anytime the color factors satisfy Jacobi identity, then so do the numerators. And anytime I flip a color factor, I do an antisymmetry, then, so two diagrams are related by flipping, well, then the numerators pick up the same sign. And then we construct an amplitude some ni, well, with the factor kappa over 2 to the n over 2. Okay, so this is another property, another expression for a candidate amplitude in gravity, right? So this is called the double copy, or the original double copy formula. Okay, so one question, is this thing gauge invariant? And the answer, well, to see this, it's convenient to consider a situation where I take one ni from one set of theories, say n equals 0, pure Yang-Mills, and another set from n equals 4. Then, if I perform a polarization vector change like this for the ni's, well, I will pick up a gauge transformation which involves the sum of delta I times ni tilde. So the m transforms to m plus some ni tilde delta I over di. So if the ni tildes satisfy this property, this color kinematics property, then this thing will just be m. Right. So I will build a gauge invariant amplitude provided my numerators satisfy the same identities as the color factors. So this thing is called color kinematics duality. Now, at the same point, if I've got external gravitons, well, they will, sorry, if I start with external gauge bosons, I'll get external gravitons because I've doubled the helicity of each particle. So this is a good way of making amplitudes in gravity as well. It's also very convenient. You can also use it when you've got massive particles. It also brings me back to this issue about the connection between color and kinematics. This really looks like a situation where gravity is a theory where you've replaced the color, it's a gauge theory, but where the color has something to do with the kinematics. That's always a tantalizing prospect, and it would be nice to know more about that, but it's still just sort of a tantalizing prospect. Okay, I won't say any more about this. It's lunchtime. I'm sure we're all hungry. Let's leave. Thanks.